We have been discussing about probabilistic algorithms which can return wrong output with a very small probability, and those algorithms are collectively known as Monte Carlo algorithms. Today we can start discussing about the other class of probabilistic algorithms known as Las Vegas algorithms. Those are probabilistic algorithms returning correct answer for every instance. Las Vegas algorithms is the topic for today. What are Las Vegas algorithms? They are probabilistic algorithms which find correct answer for every instance. So, unlike Monte Carlo algorithms, Las Vegas algorithms have zero error probability. That is a property. However, we can have two types of Las Vegas algorithms. In the first type, we have probabilistic algorithms returning correct solution for every input or instance. That is a required property about any Las Vegas algorithms. But in the second case, they may fail to find correct answer for some instances, but we can make them returning correct answer by repeatedly executing the same procedure, and that is why they are also known as Las Vegas algorithms. So, the class B or type B Las Vegas algorithms may fail to find answer for some instances individually, and that will be indicated by a return parameter, namely success, which will be set to false or true depending on whether that instance fails or succeeds. And for every instance, there is a non-zero probability of success that is guaranteed. There is a chance to get into a success case. So, what you can do is you repeatedly invoke the procedure until it succeeds in finding a solution, and when you return, the answer will be correct. So, it will also find correct solution for every instance, but may need to execute the basic procedure repeatedly until it finds a success case, because a particular instance can fail, and because we know that there is a non-zero probability of success, you repeatedly execute it. So, these are the two types of Las Vegas algorithms. Now, we can see more about the type A Las Vegas algorithms. Those algorithms with no error probability even for a single instance, and they are useful when the average performance and the worst case performance differ in a deterministic algorithm. For example, if you look at the deterministic sorting algorithm, quicksort, we know that the average case execution time is order of n log n, and the worst case is omega of n square, which happens when you give an already sorted list. So here we have a deterministic algorithm whose average and worst case performance differ in order of magnitude. In such a case, we can go for type A Las Vegas algorithms. What they do is they steal some time from a good instance and give it to a bad instance. A good instance means the instance for which the time complexity is minimum possible, and bad in the sense that the time complexity is more, maximum. So basically what they do is they will try to steal some time from such an instance and give it to a worst case instance. So some adjustments in the algorithm will try to reduce or eliminate the difference between the order of magnitude representing the complexity. And because such algorithms steal time from the good instance and gives it to bad instance, they are called, this effect is called Robin Hood effect. So basically such algorithms reduce or eliminate difference between the average performance and the worst case performance. For instance, we can have a randomized quicksort, which is a Las Vegas algorithm that we shall discuss in the next lecture, whose worst case execution time is n log n. Recall that for the quicksort, in the deterministic case, average case complexity is order of n log n and worst case execution time is omega of n square. So you need n square operations. But we can have a type A Las Vegas algorithm which always produces the correct result, whose time complexity is n log n regardless of the instance. So now in this case you can say that the algorithm that is in the randomized case is stealing some time from the best instance and is giving it to reduce the worst case complexity, and that's why both are becoming n log n. Now about the type B Las Vegas algorithms, individually you allow a small error probability, but you can repeatedly execute until you get a correct answer. So this is going to be the abstract procedure which admits some error probability. Las Vegas algorithm, it takes an input instance and y represents an output parameter, and success is also a Boolean output parameter which will be either true or false. True means you got the correct result, false means or failure means you failed in getting a correct instance. The probability of success for any instance x is non-zero, which is a guaranteed case. And you know that for Las Vegas algorithms, they need to always produce correct output, but this procedure is violating that property because there can be a failure case. Now what you can do to satisfy that requirement is repeatedly execute this procedure until you get a success. So this is what you can do. You repeatedly call this function until you get a success. And this property that there is always a non-zero probability of success, you can do it. So this is the abstract flow of control for any Las Vegas algorithm in type 2, type B. Now we can look at a problem in computer science, and we can have a type A Las Vegas algorithm for this problem. That is, we will get a correct algorithm, probabilistic but giving correct result for any input, and we will go for this probabilistic algorithm because we can see that a deterministic algorithm differ in the average and worst case execution time. And what is the selection problem? It's a well-known problem. Given a sequence S of n numbers, this S is capital S, that is the sequence, and a natural number small s, which is an index to this sequence, that is that index value should be less than or equal to n. In this sequence we have elements from 1 to n, so S is just an index or a number less than or equal to the number of elements in the sequence. And the problem is to find the the smallest element of S. Example, given this sequence with this many numbers, you are asked to find the third largest. For this instance, the answer is 24. 24 is the third largest element of the given sequence. So this is the problem. Given a sequence, find the ith largest element for a given I less than or equal to n. N is the number of elements. How we can solve this problem algorithmically? A naive solution could be, first you sort the sequence, then you return the nth element in the sorted sequence, then you will get a correct answer, no question. But then the best non algorithm takes order of n log n time for sorting, and it is not that you cannot have a more efficient algorithm. Any comparison based algorithm will take order of n log n time. So that is the naive procedure, which is deterministic, and you can have a correct solution for the selection problem. Now we can see another approach using a basic operation known as pivoting. Pivoting is a sub-process used by the quicksort algorithm. And what is pivoting? Given a sequence capital S of n numbers and a number small p in the sequence, the problem is to rearrange the sequence capital S such that in the resulting sequence S prime, you need to have the numbers placed before p less than p and the numbers that you are going to place in S prime after the number p must be greater than p. Example can make the problem very clear. Given this sequence and p as an element of the sequence, you want to rearrange these elements such that in the resulting sequence you have p, which is 31 here, not that there could be multiple occurrences of p. So you have to rearrange such that the elements that you are placing before p or 31 is less than 31. Their order doesn't matter. They can occur in any order, but every element is less than 31. And after that element, every element is greater than 31. So these are the properties. For every index I in the red set, that is from 1 to k, if you take k as the last index where you have a value less than 31, you know that in the red set the value is strictly less than p, and in the purple set the value is exactly p. So from k plus 1 to l minus 1 index, you should have p as the value. And what is the last condition? In the green set, when I is greater than or equal to l and less than or equal to n, the last index, the value at I must be greater than p, which is 31. So that is the pivoting operation. Suppose you have a procedure, namely pivot which takes the sequence and a number p as input and returns the index values k and l, satisfying these three equations. So from 1 to k you have values less than p, and from k plus 1 to l minus 1 all positions store the value p, maybe just one, but in general could be more than one. And in the green set, that is from l to n, all values greater than p. And let us assume to have such a procedure, pivot based, which you can easily write, which takes a sequence and a number in the sequence as input and rearranges the sequence and returns the values of k and l. Now recall the problem. Given a sequence, we need to find the ith largest or the th smallest. It could be largest or smallest, sorry for the confusion. So you look at the smallest, the ith smallest. So given this sequence, how we can solve the selection problem? Given sequences and a number less than the number of elements, say s, find the th smallest element. We can try to use the pivot this procedure where you are passing p as the first element of the sequence, in this case 31. And what it will do? It will give you back a sequence, modified sequence S prime, k and l, satisfying the three equations that we discussed in the previous slide. Now you want to find the th smallest depending on what is the value of s in terms of k and l. Maybe you are searching for s in the red set, which is the first sequence of element, or in the green set, last sequence of elements, or you are going to look at an element in the purple set, which is in the middle. So there are three cases. Case 1, the th smallest is what you are looking at, which you have to find from the red set, that the value of s is less than or equal to the index k. In that case, what you can do is you can reduce that selection problem to search in the smaller set, that is the red set. That is, what you do is you select, you apply the selection in the modified sequence from 1 to 3, 1 to k. So you don't have to worry about the other sequences here, only in the first subsequence. So from 1 to k you apply the selection. So it's like divide and conquer. Now in the case 2, suppose s is greater than or equal to l. So you have to find the th smallest from the second, third sequence, subsequence. So what you can do? You apply the selection problem in the green sequence. What is the green sequence? in the modified sequence from L to N. Okay, from L to N, and which is the element that you have to find? The nth smallest from this is, suppose you are looking for the 8th smallest in the original array. 8th smallest means actually the second smallest from the green set. In this case, that is going to be 58 is the second smallest from the green set. Not that you cannot just return the value at 8 because it is not a sorted sequence. So actually you have to find the second smallest from the green set, which is actually 2, the argument that you need, the second smallest from here. And how will you get that 2? 2 is nothing but 8 minus 7 plus 1. We can easily verify that it is true in general. In this set, the position that you need is S minus L plus 1. In the first set, it is S itself because it is less than K. Now the third case, that means you have to find your element in the middle sequence, and you recall that in the middle sequence each element is P, and you return the value P as the nth smallest element. And what is P? P is actually the second argument you are passing to the pivot base. In pivot base procedure, the name is P for this. In this case 31. You know that the pivot base works in such a way that in the middle sequence every element is having the value P. So you can just return it. It doesn't matter which one you return. So this is a basic idea using pivot base, and now you can write it as a procedure. This is the selection problem. Given a sequence of n elements, and you have to find the nth smallest, where s is a value less than or equal to n. And this is what we discussed. What you can do is, in the selection, first you have to do the selection in the entire array. The first index is 1 and the last index j is n. And you have to do this repeatedly until you get a success. What you do? Repeatedly. It is not type 2 algorithm. What are you doing is, you are trying to do this. You have to search either in the first set or in this last set or in the middle set, the 3 cases, once after you apply the pivot base. So that is what I am trying to do. Okay, you recall that we have selected the first element as P. The first element is denoted by I. I means the first index to the array. J is the last index to the array that you are searching. So you take P as the first element, then you call pivot base. You will get S prime, K and L. Then the 3 cases, first is S less than or equal to K. Then we found that we have to search in the first sequence, first subsequence, where you don't have to modify the first index value I, but you have to set the second index as K because you are only searching from 1 to K. And now else if suppose you have to search in the green set, we found that in that case I should start from L because you are going from L to N. So J need not have to be changed. And what is the position that you are searching for? This is what we found, S minus L plus 1. And in the third case we found that we can just return P. So we are just writing this as a procedure. Okay, and you can see that the average case execution time for this algorithm is linear in the number of elements. You can do an analysis and prove that the average case execution time is linear, but the worst case execution time is quadratic, order of n square. Thus we are getting a deterministic procedure whose average case and worst case execution time differ in order of magnitude, linear order of n and quadratic order of n square. So now we can try to get a probabilistic procedure stealing some time from the best instance, giving it to the worst instance, and in the algorithm that we are going to discuss, we can see that we will get a probabilistic algorithm which will always give the correct answer, but the expected time of execution in both the cases, average and worst, is linear. That's what we are going to see. A randomized selection using pivot base. This is the procedure. The only difference is that rather than selecting the first element in the subsequence as P, we are selecting a random element in that subsequence. Uniformly at random, you select an index between I and j, including I and j. And whatever be that index, you select that element as P. That is the only randomness. Rather than fixing the first element in the subsequence as P, select a random element from the subsequence as P. Otherwise, the algorithm is correct, same as the previous, and it can be proved that in the modified case, the expected time required by this algorithm is linear regardless of the instance. For both the worst case and average case, you are getting a probabilistic algorithm whose expected time of execution is linear. Now we are getting a linear probabilistic algorithm, linear time probabilistic algorithm for finding the S the smallest, and if you want, you can use this algorithm to find the first smallest, then the second smallest, then the third smallest, until you find the nth smallest, and thus you are getting a procedure for sorting using the solution for the selection problem. Because it is linear, this algorithm will be a quadratic algorithm. Not a very good algorithm because there are deterministic n log n algorithms, but just a procedure that you can obtain. Okay, so with this we are finishing this lecture. Today we started discussing about Las Vegas algorithms, probabilistic algorithms which return correct solution for every input or instance. They are subdivided into two classes, type A and type B. Type A always returns correct answer for every single instance, and we will get more efficient algorithm for all instances, and we can use them when the deterministic algorithm differ in the average and worst case complexity. In the type B, individual instance may fail to find the correct answer, but it is guaranteed to have a non-zero probability of getting the correct answer, and hence you can repeatedly execute the type B Las Vegas procedure until you get a correct solution, and hence finally you can get a Las Vegas algorithm by repeatedly executing a type B Las Vegas procedure. We also have discussed about a probabilistic, which is Las Vegas algorithm in the type A class for the selection problem, whose expected time of execution is linear regardless of the instance. Thank you.